is on the directional derivative of a scalar field. I also teach the tangent plane. Of course, at last, we solve a few problems on these concepts. Now, let us understand a classical definition of the directional derivative of a given scalar field. For this purpose, let us select a scalar field f from R3 to R. This function f from R3 to R can be represented as w equals f of x comma y comma z. Also, it represents a surface in the 3D space. Now, we want its directional derivative in the direction of a prescribed vector, say u cap. We very well know that dou f by dou x is a directional derivative in the direction of x-axis. Similarly, dou f by dou y and dou f by dou z are directional derivatives of f in the directions of y-axis and z-axis respectively. But here we want the directional derivative of f in the direction of the given vector, say u cap equals u1 I cap plus u2 j cap plus u3 k cap. This vector u cap can also be represented as the triplet u1 comma u2 comma u3. Now we want a directional derivative of the given surface w is equal to f of x comma y comma z in the direction of our prescribed vector u cap. Here we require the direction of u cap only but not its magnitude. So we discard the magnitude of u cap. We don't want its magnitude, so we take u cap to be a unit vector. Now let us choose a reference vector x0 comma y0 comma z0 in the domain space R3. Let this point be P. Now let us draw a curve C from this reference point or an initial point, say P x0 comma y0 comma z0 to some other vector x comma y comma z in the 3D space. The direction must be in the direction of our prescribed vector u cap. Now the curve is parameterized by using a parameter s. Now what happens? At the initial distance or displacement, x of 0 becomes x0, y of 0 becomes y0, z of 0 becomes z0. So these three give the values of x of s, y of s and z of s at s is equal to 0 at the initial displacement. After that, x of s equals x0 plus u1s, because after the displacement s, we reach the point un, so x of s becomes x0 plus u1s. From x0, we traveled s displacement in the direction of u1, so x of s equals x0 plus u1s. Similarly, y of s equals y0 plus u2s and z of s equals z0 plus u3s. The directional derivative of our scalar field f maps R3 to R in the direction of the given vector u cap equals u1 I cap plus u2 j cap plus u3 k cap is given by the formula df at u cap equals df by ds at u cap equals limit s tends to 0 f of x naught plus u1s comma y naught plus u2s comma z naught plus u3s minus f of x naught comma y naught comma z naught upon s. The symbol for the directional derivative of f in the direction of u cap is df sub u cap or df by ds sub u cap. If we carefully observe the formula of the directional derivative df at u cap for the function f from R3 to R in the direction of the prescribed vector u cap, we can understand one thing. This formula df sub u cap equals limit s tends to 0 f of x naught plus u1s comma y naught plus u2s comma z naught plus u3s minus f of x naught comma y naught comma z naught upon s resembles the differentiation formula d f of x by dx of a function of single variable in our calculus. Now, let us understand a process of finding the directional derivative of a given scalar field in the direction of a given vector. We can't apply the classical formula to find the directional derivative of a given scalar field in the prescribed direction. So we need a working process to find the directional derivative. So we have to understand the following remarks. Let us select a scalar field f from R3 to R. The directional derivative of this function in the prescribed direction u cap is given by del f sub u cap equals df by ds at u cap. By using chain rule, it can be expressed as dou f by dou x times dx by ds plus dou f by dou y times dy by ds plus dou f by dou z times dz by ds. This can be written as del f at u cap equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z dotted with I cap dx by ds plus j cap dy by ds plus k cap dz by ds. I have already written the directional derivative df at u cap as a dot product of two vectors I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z and I cap dx by ds plus j cap dy by ds plus k cap dz by ds. To evaluate this, we need to find out the values of dx by ds, dy by ds and dz by ds. Let us find out these values. Dx by ds is nothing but the derivative of x of s with respect to s. We have to use the differentiation formula for the function of a single variable here. So we have to find out dx by ds by using a formula for differentiation for the function of a single variable because x of s is a function of a single variable s. So dx by ds equals limit s tends to 0 x of s minus x of 0 upon s. Here we know the values of x of s and x of 0. X of s is x naught plus u1s and x of 0 is nothing but x naught. If we plug in these values there, we get dx by ds equals limit s tends to 0 x naught plus u1s minus x naught upon s. After cancelling x naught, we get dx by ds equals limit s tends to 0 u1s upon s. This in turn becomes dx by ds equals u1. We need to find out dy by ds and dz by ds also. Dy by ds equals limit s tends to 0 y of s minus y of 0 upon s. This again equals limit s tends to 0 y naught plus u2s minus y naught upon s. After cancelling y naught, we get dy by ds equals limit s tends to 0 u2s upon s. This gives us dy by ds equals u2. Similarly, dz by ds equals u3. Now we found the values of dx by ds, dy by ds and dz by ds. Here dx by ds is u1, dy by ds equals u2 and dz by ds equals u3. We have already found the values of dx by ds, dy by ds and dz by ds. We have to substitute these values in our previous equation 1. Then we get df at u cap equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z dot I cap u1 plus j cap u2 plus k cap u3. Now we get df at u cap equals del f dot u cap. So the directional derivative of the given scalar field w is equal to f of x comma y comma z in the direction of our given vector u cap is df at u cap equals del f dot u cap. While finding the directional derivative of a given scalar field f from R3 to R at a given point P in the direction of a given vector u cap, we follow the procedure. In this procedure, we first find out the partial derivatives of the given scalar field dou f by dou x, dou f by dou y and dou f by dou z. In step 2, we find out the gradient of the given scalar field f. Del f equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z. In the third step, we evaluate this gradient del f at the given point P. In the next step, we consider the given vector u cap. Because we want its direction only, we don't want the magnitude, we find out norm u cap. We find out a unit vector n cap equals u cap upon norm u cap. If we observe, this n cap is a unit vector and the direction of n cap and u cap are same. Now, to find out the directional derivative of a given scalar field f at a given point P in the direction of a given vector u cap, we find out del f at P dot n cap. What is a tangent plane? Consider a scalar field f from R3 to R. It can also be written as w equals f of x comma y comma z. Suppose a point P x naught comma y naught comma z naught is given on this surface. Tangent plane literally touches the given surface at this point P x naught comma y naught comma z naught. Let's see what is the equation of this tangent plane. To find out the tangent plane of the given surface at the point P x0, y0, z0, we need to find out the dot product between del f and x minus x0 I cap plus y minus y0 j cap plus z minus z0 k cap. The dot product between these two vectors gives us the equation of the tangent plane x minus x0 times dou f by dou x plus y minus y0 times dou f by dou y plus z minus z0 times dou f by dou z. This equation represents the tangent plane of the given scalar field at the given point P x0, y0, z0. We have seen the directional derivatives and tangent planes so far. Now we solve a few problems. In problem 1, they gave us a surface phi of x comma y comma z equals 4x z cube minus 3x square y square z. They gave us a point P 2 comma minus 1 comma 2 and a vector say u cap is equal to 2I cap minus 3j cap plus 6k cap. Now to find out the directional derivative of the given surface phi of x comma y comma z at the given point P 2 comma minus 1 comma 2 in the direction of the given vector 2I cap minus 3j cap plus 6k cap, we consider the given surface phi of x comma y comma z equals 4x z cube minus 3x square y square z. For this surface, we have to first find out its partial derivatives dou phi by dou x, dou phi by dou y and dou phi by dou z. In this case, dou phi by dou x equals 4z cube minus 6xy square z. Dou phi by dou y equals minus 6x square yz. Now the partial derivative of phi with respect to z is given by dou phi by dou z equals 12xz square minus 3x square y square. Now dou phi by dou x at the given point P we have to find. To find dou phi by dou x at P, we have to substitute x equals 2, y equals minus 1 and z equals 2 in the place of dou phi by dou x. Then we get dou phi by dou x at the given point P equals 8. Now we have to find out dou phi by dou y value at the given point P 2 comma minus 1 comma 2. If we substitute x equals 2, y equals minus 1 and z equals 2 in the place of x, y, z, we get dou phi by dou y at P equals 48. Similarly, dou phi by dou z at P equals 84. Now we have to find out the gradient of phi. The gradient of phi is denoted by del phi, which equals I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. Here we find out del phi at the given point P equals 2 comma minus 1 comma 2. We obtain del phi at P equals 8 I cap plus 48 j cap plus 84 k cap. Consider the given vector u cap equals 2I cap minus 3j cap plus 6k cap. Now we have to find out its length or norm. Norm u cap becomes root over 2 square plus 3 square plus 6 square, which equals square root upon 49, and it gives us norm u cap equals 7. We have to find out the unit vector n cap. N cap equals u cap whole divided by norm u cap. So n cap equals 2i cap minus 3j cap plus 6k cap whole divided by 7. This gives us a unit vector n cap in the direction of u cap. The magnitude of n cap is 1. The direction of n cap is same that of u cap. To find out the directional derivative of phi in the direction of u cap at the given point p 2 comma minus 1 comma 2, we need to find out the dot product between the vectors del phi at p and the unit vector n cap. So the dot product between del phi at p and n cap is given by del phi at p dot n cap equals 8i cap plus 48j cap plus 84k cap dotted with 2i cap minus 3j cap plus 6k cap whole divided by 7. This in turn gives us del phi at p dot n cap equals 376 upon 7. Problem number 2. In this problem, a surface phi of x comma y comma z equals x square yz plus 4x z square is given to us. We have to find its directional derivative at the point P equals 1 comma minus 2 comma minus 1 in the direction of a vector u cap. In this problem, we need to find this vector u cap. Here u cap is a normal to the surface g of x comma y comma z equals x log z minus y square. So we have to divide this problem into two types. First part is we have to find the gradient of the given scalar field phi of x comma y comma z at the given point 1 comma minus 2 comma minus 1. Next, we have to find u cap. U cap can be found by finding the normal to the surface g of x comma y comma z equals x log z minus y square at a prescribed point. Now, let us finish off the first part of this problem. That means in this first part, we find the gradient of the given scalar field phi of x comma y comma z. So in part 1, let us consider the given surface phi of x comma y comma z equals x square yz plus 4x z square. The given point P is 1 comma minus 2 comma minus 1. To find the gradient of the given surface phi, first we have to find out its partial derivatives dou phi by dou x, dou phi by dou y and dou phi by dou z. First let us find out these partial derivatives. For the given surface phi of x comma y comma z equals x square yz plus 4x z square, dou phi by dou x equals 2xyz plus 4z square. Dou phi by dou y equals x square z. Dou phi by dou z equals x square y plus 8xz. Now we find out dou phi by dou x at P, dou phi by dou y at P and dou phi by dou z at P. Here P is the point 1 comma minus 2 comma minus 1. If we find out these values, we obtain dou phi by dou x at P equals 8, dou phi by dou y at P equals minus 1, and dou phi by dou z at P equals minus 10. By using these values, we find the gradient of phi at the given point P. Del phi at P equals I cap dou phi by dou x at P plus j cap dou phi by dou y at P plus k cap dou phi by dou z at P. If we plug in the values of the partial derivatives at P, we get del phi at P equals 8 I cap minus j cap minus 10 k cap. In the first part, we have found the gradient of the given scalar field phi at the given point P 1, minus 2, minus 1. So, we want the unit vector to find the directional derivative of the given surface. For that, we need to find out a normal to another surface g of x, y, z at the another point, say Q. Consider that second surface g of x, y, z equals x log z minus y square. Let that second point be Q equals minus 1, 2, 1. Now, to find out a normal to this new surface G, we have to find out the gradient of this surface G also. For that purpose, we have to find out the partial derivatives of G. So we need to find out dou G by dou x, dou G by dou y, and dou G by dou z. For this given surface G of x, y, z equals x log z minus y square, dou G by dou x becomes log z, dou G by dou y equals minus 2y, dou G by dou z becomes x by z. Now, we have to take q equals minus 1, 2, 1. So here x value is minus 1, y value is 2, and z value is 1. We have to plug in these values in del G. Here we need to find out del G. Del G equals I cap dou G by dou x plus j cap dou G by dou y plus k cap dou G by dou z. Del G equals I cap log z minus 2y j cap plus x by z k cap. If we want del G at the given point Q, we have to substitute x equals minus 1, y equals 2, and z equals 1. If we do so, the gradient of z at the point Q, del G sub Q equals minus 4j cap minus k cap. We can suppose this vector as u cap. So we can take u cap equals del G at Q, that equals minus 4j cap minus k cap. According to our procedure, to find the directional derivative of phi in the direction of this vector u cap, that is del D at Q, we have to find out a unit vector n cap. How to find this unit vector n cap? N cap equals u cap by norm u cap. In this case, n cap equals del G at Q divided with norm del G at Q, which is equal to minus 4j cap minus k cap whole divided by root 17. This gives us the n cap. Now we have to find out the directional derivative of the given surface phi at the given point P in the direction of u cap. Here u cap equals del g at q. Now we have already found a unit vector n cap in our previous part. Now it remains to find out the directional derivative of the given surface in the direction of n cap, which is also the direction of u cap. For this purpose, we have to find out del phi at p dot n cap. This gives us the required directional derivative. So del phi at p dot n cap equals 8i cap minus j cap minus 10k cap dot minus 4j cap minus k cap by root 17. The dot product is 14 by root 17, which is the required directional derivative of the given surface in the direction of the normal to the second surface g of x comma y comma z equals x log z minus y square at the point q. We are done. Problem number 3. In this problem, we have to find out a tangent plane to the given surface at the given point. In this problem, the given surface is xz square plus x square y equals z minus 1. The given point P is 1 comma minus 3 comma 1. To find out the tangent plane to the given surface at the given point 1 comma minus 3 comma 1, first let us consider f of x comma y comma z equals xz square plus x square y minus z plus 1. This is our given surface. Let the given point P be 1 comma minus 3 comma 1. Suppose that x naught equals 1, y naught equals minus 3 and z naught equals 1. To find out the tangent plane, first we have to find out the partial derivatives dou f by dou x, dou f by dou y and dou f by dou z. In this case, dou f by dou x becomes z square plus 2xy. Dou f by dou y equals x square. Dou f by dou z equals 2xz minus 1. Now we have to find out dou f by dou x at the given point P, dou f by dou y at the given point P and dou f by dou z at the given point P. Dou f by dou x at P equals minus 5, dou f by dou y at P equals plus 1 and dou f by dou z at P equals 1. Here in this case we get these values by substituting x equals 1, y equals minus 3 and z equals 1 in the partial derivatives of f. Now we have our formula of the tangent plane. The tangent plane formula is x minus x naught into dou f by dou x plus y minus y naught into dou f by dou y plus z minus z naught into dou f by dou z. If we plug in all our values in this tangent plane formula, we get the tangent plane to the given surface at the given point is minus 5 times x minus 1 plus y plus 3 plus z minus 1. If we simplify this value, we get minus 5x plus y plus z plus 7. We can also equate this to 0. That means our tangent plane equation may be minus 5x plus y plus z plus 7 equals 0. Thus we can find out a tangent plane to the given surface at the given point. We are done. In this lecture, we have learned the directional derivatives and the tangent planes. We solved a few problems also. For further queries, you can contact me. Thanks for listening.